Hello there! This video is going to cover the practice problems for the chi-square test of goodness of fit and the chi-square test of independence. And this will essentially take the place of the end of the practice day, the lecture that I usually give you guys, but I'm not there, so you're going to watch this video instead. So you're looking at the key right now, and hopefully you've already attempted these practice problems on your own. Hopefully you attempted these practice problems with your fellow classmates too and have discussed them already before watching this video. So the difference between a chi-square test for goodness of fit, chi-square test for independence, both two different ways. So one way that they're different is what the data look like, and the other is what conclusions can be drawn. So for goodness of fit, you have data that's from a single variable. Or when you look at the setup for a chi-square test for goodness of fit, you have a single row with however many columns that you're interested in, because you only have one independent variable with multiple levels of that independent variable. Now, the conclusion that's made from the chi-square test of goodness of fit is to see if there's a discrepancy in the frequencies or proportions between the data and the null hypothesis. And remember, the null hypothesis can be that there's no difference at all, essentially the same frequencies for each group, or the null hypothesis can be based on specific proportions from the population, and you're testing to see if the proportions of the frequencies in each group in your sample match or don't match the proportions that you would expect based on the population, or the frequencies that you would expect based on the proportions in the population. Now the chi-square test for independence, that is it comes from data from two variables. So you would have multiple rows and multiple columns, however many levels of each independent variable you have. So the initial setup for that one looks similar to the two-factor ANOVA, and then the initial setup for the goodness of fit looks kind of similar to a single-factor ANOVA. Now, the test for independence is essentially doing a correlation analysis with frequency-based data, and you're seeing if the two variables are independent of each other, or if there's a relationship between the two variables. Now, this next example problem. So, I'm going to go ahead and do the calculations. You see all the work here, but I'll go ahead and work through them in a smart notebook page so that you can see each step of the calculation, easier than just looking at it on the screen. But for this one, Laura is doing some research, and she thinks that there's an equal number of Democrats and Republicans among faculty members at Nevada State College. So she's going to collect data on 200 faculty members and ask them, are you a Democrat or are you more of a Republican? And her data looks like this. 125 said Democrat, 75 said Republican, 200 is her entire sample size. Now, one thing I want to mention. Traditionally, the null hypothesis goes against our expectations. But that's because typically our expectation is that there is a difference. But in this example, she doesn't think there's a difference, right? So her expectation is that there is an equal number. But the null hypothesis is still that there's an equal number, or that the distribution is the same, because the null hypothesis is always saying there is no difference. It's just this time she's expecting the null to be true, and that's kind of rare. Then the alternative, the distribution of Republicans, is not the same as the distribution of Democrats. Now, if you are confused about stating the null and alternative, you could just kind of steal from this, and you could say the null would be that there is no significant differences in the number of Democrats and Republicans among all faculty members at NSC, and the alternative would be that there is a significant difference in the number of Democrats and Republicans among all faculty members at NSC. That's totally fine with me. And this says among all faculty members because we are using this sample to make inferences about the population. All right, let's go ahead and take a look at the calculations. So I'm going to steal this and put it into a notebook here. All right, so remember the formula for the chi-square is, well, actually, let's go back and do the critical value real quick. I'm getting ahead of myself. Okay, chi-square crit, degrees of freedom is 1, because our degrees of freedom is equal to C minus 1. We have two columns. 2 minus 1 is 1. So when you go and you look up the critical value in the table, let's get that for you guys. The last table here. Proportion in critical region, alpha level is 0.05, degrees of freedom is 1, 3.84 is your critical value. And you'll see that. Wait a tick. I think I had my alpha level incorrect. Oh, looky there. Be careful. So your alpha level is 0.01. I just automatically assumed 0.05, but you need to be careful. Check your alpha level. All right, now we're back on track. Alpha level 0.01, degrees of freedom 1. There you go, 6.63. All right, now let's do some calculations. So the first step is we need to figure out the frequencies expected for each one of these. So there's two ways you could do this. You could do the PE times N. And remember, the PE is equal to 1 divided by the number of columns, so 1 divided by 2. And then N in this case is 200. So this would be 0.5 times 200 equals 100. Or we could just say N divided by the number of columns, which is 200 divided by 2. You still get 100 for both of these. Now, these frequencies expected, so these are our frequency observed. These frequencies expected are the exact same value because our null hypothesis is stating there's no significant difference. If we had specific population proportions, we wouldn't have this case, and we would only be able to use this formula to figure out the frequency expected, and each PE would come from the proportions from the population. But we're going to use the more simplistic form of this, and this is also what you can expect to see on the quiz, will be this kind of hypothesis. Okay, so now we need to do our chi-square calculation based on our observed and expected frequencies. Chi-square is equal to the sum of each observed frequency minus the relative expected frequency squared divided by the expected frequency. So, for our first group, our Democrats, the observed frequency was 125. We expected 100. And for the Republicans, and we're putting a plus sign here because we're adding, we're doing summation, we observed 75. Under the null hypothesis, we expected 100 squared divided by 100. So we end up with 25 squared divided by 100 plus negative 25 squared divided by 100. Well, 25 squared gives you 625. So 625 divided by 100. And negative 25 squared also gives you 625 because a negative times a negative is a positive. And 625 divided by 100 is equal to 6.25. And you end up with a chi-square for goodness of fit of 12.5. Now when you take that 12.5 and you compare it to the critical value, (12.5) versus 6.63, 12.5 is much larger, so you can reject the null hypothesis. Results suggest the distribution of Democrats and Republicans is significantly different among NSC faculty. So we supported the alternative hypothesis. Not the same, it's significantly different. So make sure in your conclusion that you mention the word significant, whether or not it is significant. You mention the groups that are the basis of your chi-square test for goodness of fit. And then you mention, let's see, results distribution of Democrats and Republicans is significantly different among who we're looking at, our NSC faculty. Okay, now let's look at the chi-square test for independence. So in this example, CSN wants to test the effectiveness of a time management workshop on a sample of students. So they randomly select a group of students and send them invitations to participate in a time management workshop. So 300 attended the time management workshop. And then they also compare that 300 who attended the time management workshop to a group of 300 who did not attend the time management workshop. And they call this the control group. So out of those who attended the workshop, those 300 who came, 190 were successful. They received a C or higher in a randomly selected course the next semester, and 110 were not successful. And we're calling not successful. They got a C minus or lower. They withdrew from the randomly selected course following the workshop. Then of those who did not attend, 120 were successful. They received a C or higher, and 180 were not successful. Now, notice that here you've got your table, and it's based on the explanation of the study. So you could say, okay, 125 were Democrat, boom, 125, 75 were Republican, put that there. You could also do the same with this. You don't have to have this table. You could use the description to put your data in a table, but you always want to end up with data in a table so that you can do your calculations. All right, so the question is, do the data suggest there's a significant relationship between the time management course and student success? Now, there's multiple ways you could write your alternative hypothesis for this. One, the distribution of success is equal for both groups. That's fine. Or there is no relationship between participation in the time management workshop and success. I prefer that one because it's like the interpretation of the correlation, and that's something we're all familiar with. Or you could say time management workshop and success are independent. Then the alternative, the same thing, except for now we're saying it's not equal for both groups, the distribution of success. There is a relationship between participation in the time management workshop and success, or the time management workshop and success are dependent. So I would opt for these two for your null and your alternative, the one that's based on a relationship. Just because, again, it's something you've been exposed to, it's probably easier to remember. So I'm going to go ahead and steal this data and put it into a notebook page so I can manually go through the calculations for you. All right, I'm going to make this a little bit smaller too. Okay, so now I need to find my expected frequencies. And I'm going to go ahead and use the formula that looks like this. So the frequency for the column times the frequency for the row divided by the sample size. And in all these cases, my sample size is 600. So that'll be constant for all of these calculations. All right, so let's go ahead and recreate this table, in a way, with our calculations. So we're going to have attended the workshop, not attended the workshop, just abbreviating here. We're going to have success, and we're going to have not success. All right. So these are our frequency rows. These are our frequency columns. And what you're doing is, for this one, we're looking at the frequency for this row times the frequency for this column and dividing it by the sample size. So we would have 300 times 310 divided by 600. And 300 times 310 gives us, let's see, 300 times 310, 93,000. Oh boy. Divided by 600, and you get 155. Then the next one. So we're still working with the same column. We're going to have a different row. So now we're going to have for our column, and this is actually the frequency row. I did them a little bit backwards. Sorry about that. Okay, so now we have 310 times 300. And that's going to be the same thing as before, 155. Now the reason that these two are the same is because we have an equal number of those who attended and those who did not attend. In the lecture, the practice problems, the example problems, they weren't the same because you had a different sample size for each group. Okay, so now we're looking at the not successful among those who attended the workshop. So the frequency for that column is 290 times the frequency for that row of 300 divided by 600. Okay, so we have 290 times 300 equals 8,700 divided by 600, and you get 145. And once again, we're going to have the same expected frequency for the not successful students who did not attend the workshop because we have the same frequency column and we have the same frequency row because we have an equal sample size. So 145. All right. And to double check your work, you could add these two together and you get 300. You could add these two together and you get 300. You can add these two together and you get 310. Add these two together and you get 290. So your marginal frequencies, your frequency rows and your frequency columns should be the same. And this looks like FE. It's not. It's FC, just to be clear. Okay, so now we have all the values that we need to figure out our chi-square statistic. So chi-square equals the sum of the frequency observed for each group minus frequency expected squared divided by frequency expected. All right, so we have for our first group our successful students who attended the workshop. We observed 190 of those. We expected 155. Then my next group, the successful students who did not attend the workshop. We observed 120 of those. We expected 155 if the null hypothesis was true and there was no relationship between time management workshop and success. The next group, those who were not successful that attended the workshop. We observed 110 of them. We expected 145. And then my last group, those who were not successful who did not attend the time management workshop. So we had 180 of them. We expected 145. Don't forget to do your squaring and all that. All right, so 120 minus 155 gives you, 190 minus 155 gives you 35. Don't forget your square, and then we're going to divide it by 155 eventually. Right now I'm just solving for the parentheses. 120 minus 155 gives you negative 35 squared. 110 minus 145 gives you, oh wow, this is going to work out nicely, negative 35 squared divided by 155, right? Oh, denominator is 145, silly. So 145 plus 180 minus 145 is 35. I'm going to square it, divide by 145. Well, 35 squared is equal to 1,225. So 1,225 divided by 155 plus 1,225 divided by 155 plus 1,225 divided by 145 plus 1,225 divided by 145. 1,225 divided by 155 is equal to 7.903. And we have two of those because we have two of those. Plus 1,225 divided by 145 gives you 8.448. And we have two of those because we have two of those. And you end up with a chi-square statistic of 32.702. That is pretty large. The data does not fit the null hypothesis very well, so I'm inclined to say, hey, it does exceed. Oh, let's go back. So my 32.703 does exceed my critical value right here. And I kind of neglected the critical value. I jumped right to calculations. So let's take a look at that. So our degrees of freedom is equal to R minus 1 times C minus 1. How many rows do we have? 2 rows. So 2 minus 1. How many columns do we have? 2 columns, right? Successful, not successful. So we have 1 times 1, and we end up with 1 for our degrees of freedom. And our level of significance, or our alpha level in this case, is 0.05. So 0.05, 1 degree of freedom. Found that earlier incorrectly when I didn't know we were looking at 0.01. 3.84. Okay, so yes, our calculated chi-square is greater than our chi-square crit. So we reject the null hypothesis, and results suggest that there is a significant relationship between participation in the time management workshop and success. You could really, once you reject the null, you just restate the alternative hypothesis and just go with whichever result suggests statement that you chose. Alright guys, sorry I couldn't be there today to help you go over the practice problems, and sorry I kind of rushed through this video. But times are kind of crazy. I hope this helped. I hope you feel confident with chi-square, and I hope that you are ready to do your discussion day and then be prepared for the review day that happens after Thanksgiving.